Okay, so in this video, we want to consider an application of the first and the second derivative in trying to help us sketch the graph of any function y equals f of x. Now there'll be a bit more to it than just the first and the second derivative, but we'll see at least what we get as far as the information about the graph of the function y equals f of x from the first and the second derivative. And this will justify why we care about higher derivatives, namely in this case the second derivative. And with what we'll develop as techniques, we'll be able to sketch the graph of any function using the first derivative, the second derivative, and a basic understanding of limits. So let's ask the first question. What does the first derivative tell us about the graph of y equals f of x? So remember that the derivative is the slope of the tangent line, and the slope is just the rate of change, right? So if the derivative is positive, the slope of the tangent line to the function is positive. Therefore, the tangent line is increasing. Therefore, the function is increasing. So if f prime of x, or y prime, so if y prime, which is the same as the derivative of f, so if this is greater than 0, we know that the derivative is positive, and if the derivative is positive, the rate of change of the function is positive. Therefore, the function is increasing. Well, what if the derivative is negative? So if y prime, the derivative of y, f prime of x, is less than 0, then the derivative is negative, therefore the slope of the tangent line to the function is negative, therefore the tangent line is decreasing, therefore the graph of y equals f of x is also decreasing. And there's one last option. Maybe the derivative is equal to 0. So what if you have a value of x where the derivative is actually equal to 0? Well, again, the derivative is the rate of change of the function, which is also the slope of the tangent line. So if the derivative is 0, the tangent line to the function is horizontal, so the curve at this point is flat. If you think of it as the rate of change, if the rate of change is 0 at that point, at x, then the function is not changing, therefore the graph will be flat at that point. So then the graph of y equals f of x is flat. And that's what the first derivative tells you. The derivative of y equals f of x is the rate of change. If the derivative is positive, the graph of y equals f of x is increasing. If the rate of change, the derivative, is negative, the graph of y equals f of x is decreasing. And if the derivative of y equals f of x is 0, the rate of change is 0, therefore the function is not changing, and so the graph of y equals f of x is actually flat. The question is this enough information coming from the first derivative to allow us to accurately sketch the graph of the function y equals f of x? And the answer is actually no. Let's look at the first case. Suppose that the derivative was positive. Therefore, the graph of the function is increasing. Well, imagine in how many ways can you sketch an increasing function? It could be increasing like this, or maybe it could be increasing like this. And these are two very different curves, right? This is increasing in a different way that this is increasing. And the same for decreasing, right? I could sketch a curve that is decreasing like this, or I could sketch a curve that is decreasing like this. So the first derivative does not tell you the shape of the function. If y prime is positive, the graph of the function is increasing, but it could look like this, or it could look like this. If the first derivative is negative, we know the graph will be decreasing, but it could look like this, or like this. Both are decreasing. So the question is, well, what could help us capture not only increasing versus decreasing, but also the overall shape of the curve? Let's make a definition first, and this is what we call concavity. And concavity is just exactly that. What is the shape of the curve? Is it going like this, or is it going like this if it's increasing, or is it going like this, or like this if it's decreasing? And there are two types of concavity. There is concave up and concave down. So concave up, it could be concave up and increasing. This is concave up and increasing. It could be concave up, or concave up and decreasing, or we could be looking at a point where the curve is concave up and the derivative is 0. Therefore, at that point, the curve will be flat. So it could look something like this. So this is concave up, and this is the point where the derivative is 0. Therefore, the tangent line is horizontal. So when we say concave up, it's one of these three options. But the curve, as we saw, could also be concave down. And that's the opposite of concave up. So the curve could be concave down and increasing. You see, this is increasing but concave up. Increasing but concave down would look something like this. This is increasing now but concave down. Or the curve could be decreasing and concave down. So decreasing and concave down. Or again, right, the derivative here would be positive. The derivative here would be negative. If you look here, the derivative here would be positive. The derivative here would be negative. And the derivative at this point would be equal to 0. So the curve could be concave down and increasing, a positive derivative, concave down and decreasing, negative derivative, or we could have concave down around a point where the derivative is 0. Therefore, at this point, again, the curve is flat, and so we have a horizontal tangent line. So you see that the first derivative does not capture concavity, because even though the first derivative may be positive, therefore increasing, the graph could be increasing and concave up, or also increasing and concave down. Suppose the first derivative was negative, then the graph would be decreasing. But is it decreasing concave up or decreasing concave down? And so you see, with the first derivative alone, we will not be able to know whether the curve is concave up or concave down. So the first derivative is not enough. Let's ask now, what could possibly tell us whether the curve is concave up or concave down? Let's look at, and the argument you'll see is the same whether you have this part, or this part, and the same for concave down. We'll assume that we have this for concave up, this for concave down. So suppose we have a curve that's concave up, And it looks something like that. Let's look now at the progression of the derivative as we go from left to right. So we are going to, on this line, look at values of the derivative, our dy over dx, or if you prefer, y prime, or then again, f prime of x. Start from the left. Take this point, draw its tangent line. So at this point, the derivative is clearly negative, and it's rather large and negative. So the derivative would be a value here, right? The derivative could be negative 10. Let's move a little further to the right. This was our first position. If you move a little further to the right and draw the tangent line to the curve, you see it's still negative, but it's not as steep as the initial tangent line. So this will be a slightly smaller negative number. So we're moving a little closer to 0. And this is the second value of our derivative. At this point, the tangent line is horizontal, so the derivative is equal to 0. So you see it's getting a little bigger. Move even further to the right, say take this point, draw the tangent line, and if you notice, now the line is increasing. Therefore, the derivative is now positive, so even a little bigger. And if you move even further to the right and draw the tangent line at this point, you can see that it's still increasing, but it's even steeper than this line, so the derivative here is even bigger than the derivative here. So we get an even larger value of our derivative. And look at that. Look at what's happening to the derivative as we move from left to right along a curve that is concave up. The derivative was very large and negative, then it was still negative but a little smaller, then it was 0, then we kept going to the right, it was positive, so even bigger, more to the right, positive and even steeper, so an even bigger value. So you see as we went from left to right, the value of the derivative got bigger. It was negative, it was a little bigger, little bigger, little bigger, little bigger. So you see, if you have a curve that's concave up, the derivative is increasing. As you move from left to right, the values of the derivative are gradually getting bigger and bigger. So they're increasing. So concave up means that the derivative is increasing. So dy over dx is increasing. But now think of it. dy over dx is itself a function of x. If a function is increasing, its rate of change is positive, it's getting bigger, therefore the derivative of this function must be positive. A function can only be increasing if its derivative is positive, so the derivative of the derivative must be positive. And you say, well, wait a second. We have a curve that's concave up. If the derivative is increasing, so it's getting bigger as we move from left to right, but a function is increasing if its derivative is positive. But what's the derivative of y, if not simply the second derivative? And that's it. You see that now, if the second derivative of a function is positive, the curve has to be concave up. So concavity, at least concave up, is given by the second derivative. So if y double prime, which is the same as f double prime of x, which is the same as d squared over dx squared of y is positive, the curve is concave up. And you see that the second derivative gives you concavity. Well, I'll let you check for yourself. If you draw a curve that's concave down, you will notice that the derivative is decreasing. You can imagine that if the curve looked like this, you'd have a very, or actually let's just do it right now, you'll see it will take a second. If the curve now was concave down, start from left to right and look at the progression of the derivative. Take this point, you have a very steep line with positive slope, the derivative is very big. Move to the right, the derivative is still positive, but the curve is not as steep, so the derivative got a little smaller, it's decreasing. Move even further to the right, the derivative now is 0, so it went from a positive value to 0, it's still decreasing. Move even further to the right, and the derivative went from 0 to now a negative value. So we have a big positive value, then a smaller value, then we got 0, then even smaller because now we have a negative value. And so you see when the curve is concave down, the derivative is decreasing, therefore its rate of change must be negative, but the rate of change, as we said, is just a derivative. So because the derivative is decreasing, its derivative must be negative. But the derivative of the derivatives, as we have just said, is the second derivative. And so the second derivative gives you the shape of the graph of y equals f of x. So if the second derivative of our function is now negative, then the graph of y equals f of x is concave down. And that's why the second derivative is so crucial to sketching the graph of a function. If all you have is the first derivative, all you know is whether or not the graph is increasing or decreasing, but you don't know the shape of the graph. And that's given by the second derivative. If the second derivative is positive, the graph will be concave up. If the second derivative is negative, the graph is concave down. So let's look now at the four possibilities, whether or not the first derivative is positive, negative, and the same for the second derivative. And then we'll know what the graph looks like. So suppose that the graph of the function, we wanted to sketch a graph over an interval of x values. Suppose that the first derivative is positive and the second derivative is also positive. This tells us that over this interval, suppose it is over positive x values. Suppose it's around here. If over here the first derivative is positive, the graph is increasing. If the second derivative is also positive, it is also concave up. And the only way to have an increasing function that is concave up is if the graph looks something like this. Well, there's another case. What if the first derivative was positive, but now the second derivative was negative? Well, the curve is still increasing because the first derivative is positive, but now the second derivative is negative, therefore the curve is concave down. And the only way to write an increasing function, to sketch a graph of an increasing function that is concave down, is if it looks something like this. So that's for increasing when the derivative is positive. Well, what if the derivative is negative? Well, the first derivative could be negative, and now the second derivative could be positive. Well, if the first derivative is negative, the graph will be concave down, and the second derivative is positive means that the curve is concave up. So the graph is decreasing because the first derivative is negative. So we have to sketch a graph of a function that is decreasing and concave up. The only way of doing this is if the graph looks something like this. First derivative is negative, decreasing, and second derivative is positive, concave up. And then we have our fourth and final case. What if the first derivative is negative and the second derivative is negative as well? Then our graph will be decreasing because the first derivative is negative, and our graph will also be concave down because the second derivative is negative. And the only way to sketch a graph of a function that is decreasing and concave down is if it looks something like this. So you see, with the help of the first and the second derivative, you will be able to sketch very accurately the shape of the graph of the function y equals f of x. There are two things now worth mentioning, and those are the special points in the graph of a function. There are two kinds of really important points, and those are called the critical points and the inflection points. So think of it. Suppose that the function is nice enough and the first derivative and the second derivative are both continuous. Then if the derivative, say, is positive, the function is always increasing, nothing ever changes. If the derivative is negative, the function is decreasing, nothing ever changes. But then you ask yourself, well, at which points could you expect the curve to go from increasing to decreasing or decreasing to increasing? Well, if the derivative goes from positive to negative or negative to positive, by continuity, there must be a point where the derivative is 0 or maybe undefined. And those are the so-called critical points. So if x equals x0, so we have a value of x, which is, say, x0, is such that either the derivative at this point is equal to 0, or the derivative of the function at this point is undefined, we say that x0 is a critical point of the function. And we use the word critical because those are really critical points. They're really important points. Because again, think of what you want from the first derivative. You want to know where the curve is increasing or where it's decreasing. So as long as the first derivative is positive, the graph is increasing, nothing will change. As long as the derivative is negative, the graph is decreasing, nothing will change. The only way to observe a change in increasing to decreasing or from decreasing to increasing is if you find a point, a value of x, where the derivative is either 0 or maybe undefined. And those values are really, really important. Because at those points where the derivative is either 0 or undefined, there may be a change in increasing to decreasing or decreasing to increasing. So those are really, really important points. That's why we say that they are critical points. But there's also another possible type of really important change. Concavity may change as well. So the curve could go from concave up to concave down, or concave down to concave up. Those are also really important points of the sketch of a graph. So we will call those inflection points. So we say that x equals x0, so a value of x is an inflection point if at this point concavity changes. If there is a change in concavity at this point. Because again, we want to capture the graph accurately, so we want to know where it's concave up and where it's concave down. So if there is a value of x, say x0, where there is a change in concavity, therefore if the curve goes from concave up to concave down, or concave down to concave up, we call the point an inflection point. And you may ask, well, how do we find inflection points? Well, in the same way in which we find critical points. Think of it. What gives concavity? That is the second derivative. If the second derivative is always positive, the curve is always concave up, and that's it. If the second derivative is always negative, the curve is always concave down, and that's also it. So the only way to have a change in concavity is if you have a point where the derivative is 0, or where not the derivative, sorry, but the second derivative is 0, or where the second derivative is undefined. And this is our conclusion with inflection points. So if x equals x0 is an inflection point, then the only way to have an inflection point, again, an inflection point is a point where concavity changes, and the only way to have a change in concavity, concave up to concave down to concave up, is for the derivative to change sign. So it has to be a point where the derivative is 0 or undefined. So then, not the derivative, but the second derivative, sorry, then either the second derivative at this point equals 0, or the second derivative at this point is undefined. Now, one thing is worth mentioning here is sometimes you will find fake inflection points. So you'll look for the second derivative to be equal to 0, or the second derivative to be undefined, and you may get several values of x. And not every one will give you a change in concavity. So sometimes you will get fake inflection points. But the key is if there is a point where concavity changes, so if there exists an inflection point, it has to be satisfying one of these two conditions. It has to be a value where the second derivative is 0, or where the second derivative is undefined. In the same way where the function goes from increasing to decreasing, or vice versa, must happen at a critical point, therefore a value of x, where the derivative is 0, or the derivative is undefined. And surprisingly, Once we figure out what happens to the sketch of the graph of a function around critical points and around inflection points, we will essentially get the full picture of the graph of y equals f of x. One last little definition / observations, and that is two special types of critical points where the derivative is 0 depending on whether you have concave up or concave down. This is also really important, and it will be even more so when we look at optimization. Suppose that we have a critical point where the derivative is 0, not undefined, but 0. So suppose that you have the following set of axes, and suppose that the point x0 is positive. In both cases, we'll also assume, just for clarity of the picture, that the y values of the function are positive. Suppose that the first derivative at x0 is equal to 0, so that x0 is a critical point where the derivative vanishes. Same thing here. So x0 is in both cases a critical point, a point where the derivative is 0, therefore the tangent line is horizontal, therefore the curve is flat at this point. Now suppose that, in this case, the second derivative at this point is positive, so around this point the curve will be concave up. And suppose that in this case, the second derivative at x0 is negative, therefore around x0 the curve will be concave down. Now think of it. There's not many ways you can sketch the curve, the graph of a function, at 0 where the curve is flat and that is concave up. Suppose that the y value is here in both cases. Think of it, the only way to have a curve that is flat at x equals 0, at x0, and whose concave up is if the curve looks something like this. This is the only way to have a curve that is concave up and at the point x0 to be flat, because the derivative at this point is equal to 0. And think of now this case. The curve is flat because its derivative is 0 at this point, but now it's concave down. There's only one way of sketching this. It has to look like this. And why are those important? Look at this. When the derivative is 0 and the second derivative is positive, the curve has to look like this around the point x0. But what's special about this point is it is a minimum value of the function. Look around x0, and around x0 the function attains its smallest y value at this point. And this is what we call a local minimum. Local because we are looking only around the point x0. Maybe the function can go like this and later will drop back down, so we may be getting even smaller values later down the road. But if you only look around x0, so locally, local means close to, so if you only look for values of x that are close to x0, you see that the function attains its smallest value at x0, and that's why we call this point a local minimum. Now look at the second case. If the derivative at x0 is equal to 0, the curve is flat there. The second derivative is negative, therefore the curve is concave down. Then if you look around the point x0, you see the opposite. The curve reaches its maximum value at x0. You see, around x0, the largest y value is exactly the one at x0. Any other y value is a little smaller. So if you look around this point, the function attains its maximum value at x0, and so we call this a local maximum. And local because maybe the function goes down and then comes back up, and you may get even larger y values. But if you only look locally around x0, so you stay very close to x0, you see that the maximum value of y is attained exactly at x0. And this is why we call this a local maximum of the function. And with these ideas, and using limits to find asymptotes of the function, if there are any, we will be able to sketch a graph of any function. And all we need are the first and second derivatives. We will look for the critical points, points where the derivative is 0, where the curve could go from increasing to decreasing or vice versa. Then we'll use the second derivative to tell us whether the curve is concave up or concave down. And we will look for values of x where the second derivative is 0 or undefined to see where we may have a change in concavity. And with this, we now have all the tools to sketch any possible function you can think of. And so in our next videos, we will sketch functions. We will sketch a graph of functions using our knowledge of the first and the second derivative.